A light source appears located over the center of a circular table of diameter 4. We have to find the angle alpha such that the illumination I at the perimeter of the table is maximized, so around the edges. And we're given that illumination is given by 2 sine of alpha over s squared, where s is the slant height and alpha is the angle at which the light strikes the table. Okay, so this is an optimization problem involving trigonometry. So the key to this is that we're going to want to write the entire equation in terms of alpha, because that's what we want to optimize. So we need to get rid of this s. Once we write it in terms of alpha, we'll optimize it by taking the derivative and setting it equal to 0. So first we have to notice that since the whole diameter is 4, each of these sides of the right triangle, if you just look at one right triangle, sorry that's not a very good tracing, that's a right triangle, each of those is going to be 2. So in order to use an expression to write s in terms of alpha, we need to use the trig equation that cosine of alpha is equal to 2 over s. Solving for s by cross multiplying, or whatever algebra you like best, we get s equals 2 over cosine of alpha. So that means that our illumination is 2 sine of alpha over, instead of s squared, it's going to be over 2 over cosine of alpha squared. So let's simplify this. This is 2 sine of alpha divided by 4 over cosine squared of alpha. Okay, so we're going to need to flip and multiply. So this is 2 sine of alpha over 1. And then instead of dividing by 4 over cosine squared alpha, we're going to multiply by cosine squared alpha over 4. So we get 2 over 4, or 1/2 sine of alpha times cosine squared of alpha. Okay, so as I said earlier, we need to optimize this equation. So that means finding the derivative and setting it equal to 0, or finding where it's undefined. But this one will not be undefined because sine of alpha and cosine squared of alpha are never undefined. So we're going to take the derivative. This is going to require the product rule. So the coefficient 1/2 stays out front, and then we are going to take the derivative of sine of alpha is cosine of alpha, and then we leave our cosine squared alpha alone, plus the 1/2 sine of alpha, leave that one alone, and we take the derivative of cosine squared. So I'm going to think of that as cosine quantity squared, so it's a little mini chain rule. We can, so think about that as cosine of alpha squared. So I can bring down the 2, subtract 1, and then I have to multiply by the derivative of cosine alpha. So I get 2 cosine alpha times negative sine of alpha. Okay, see a little cancellation that can happen there. So we get 1/2 cosine cubed of alpha plus, actually it's going to be a negative sine squared alpha cosine alpha. Okay, so if I want to find where the derivative is either 0 or undefined, again, let me just say that this will never be undefined because of the nature of these functions. So I really just want to find where this is 0. So I need to somehow factor this. So I'm going to notice here that I can pull out a cosine of alpha so that's my greatest common factor out of both those terms. So cosine of alpha comes out, and I'm left with 1/2 cosine squared alpha minus sine squared of alpha. Okay, so what I'd like to do now is, if I'm going to do any kind of solving, I don't really want to have both cosine squareds and sine squareds in here. So I want to rewrite the sine squared using a Pythagorean identity. So remember that sine squared plus cosine squared equals 1. That's our Pythagorean identity. So solving for sine squared is equal to 1 minus cosine squared. So I'm just going to replace my sine squared with 1 minus cosine squared. Okay, so let me rewrite. We get cosine of alpha is equal to 1/2 cosine squared alpha. I'm going to distribute my negative 1, and plus cosine squared alpha. So I have some like terms here. I have a cosine squared alpha, and I have a 1/2 of a cosine squared alpha. Adding those together, I get 1.5 cosine squared alpha. So this is 3/2 cosine squared alpha minus 1, and a cosine alpha out front. Okay, so I have a product of 2 terms equals 0. So by the 0 product property, I have that either cosine of alpha is equal to 0, or 3/2 cosine squared alpha minus 1 is equal to 0. Okay, I'm looking for all solutions that make sense in the terms of this problem. Remember, alpha is this angle of the light hitting the table. So my solutions to this equation in general would be things like pi over 2 or 3 pi over 2. But you can't have, let's look back up at the picture here. Pi over 2 is like a right angle. You can't have this angle being a right angle over here and also a right angle over here. Light can't both simultaneously be above both edges. So, and 3 pi over 2 is the same idea. It doesn't make sense. So these are both considered extraneous solutions in this problem. Sorry, as I scroll down. And so we're going to ignore those solutions. Over here, we're looking for, if I solve for cosine squared, we get 1 equals 3/2 cosine squared of alpha. Multiply both sides by 2/3. And then I'm going to need to take the square root. So plus or minus the square root of 2/3 equals cosine of alpha. So to solve for this equation, we could take the inverse. So alpha is going to be the inverse cosine of these values, plus or minus the square root of radical 2 over 3. But since alpha must be in quadrant 1 in order for this to make sense, the only value we're going to have, the only value we're going to have is the inverse cosine of the positive radical 2 over 3. And the whole thing's in the square root, sorry. Okay, so we can use a graphing calculator for this. I've already done it ahead of time, so we see that the inverse cosine of radical 2/3 is 0.615. So alpha is 0.615 radians. Okay, so now technically we need to make sure we have found a maximum. So we can do a little investigating and test values to see what's happening. So it does turn out, if you do a little bit of work, that the derivative I prime is positive before for values less than 0.615, and it's negative for values after. So that tells us the graph is first increasing and then decreasing. So that tells us that we have a local maximum at alpha equals 0.615. So that is going to be our optimal value for the light to hit the perimeter.